students, welcome back in this lecture of the vector integration. Now this is my last lecture of this unit. Now today I will discuss about the Green's theorem for a plane, and then we will solve few questions based on this Green's theorem. So our statement is Green's theorem for plane. Your statement, let's see, is the regular closed curve in the xy plane and R is the region bounded by this closed curve. Then this line integral m dx plus n dy is equal to the surface integral in the plane del n upon del x minus del m upon del y into dx dy. So your line integral is equal to the surface integral, where your mxy and xy are continuous differentiable function, where your mxy and nxy are continuous differentiable function inside and on C. So this is your statement. If C is the regular closed curve in the xy plane and R is the region bounded by this closed curve C, then this line integral is equal to this surface integral. So proof. Okay. We know that the integral by Stokes theorem, we know that the line integral C f dot dr is equal to curl f dot n ds. This is your Stokes theorem. Now let us assume the value of f so that we can have this left hand side. For that, let us assume f equal to mi plus nj. Now in this case your f dot dr, now your dr will be dxi plus dyj. So therefore your f dot dr will be equal to m dx plus n dy. So this is your line integral. Now what about the surface integral? Now for that we need your curl f. Now let us evaluate the curl of f. This is equal to I, j, k. Then we will have del upon del x, del upon del y, del upon del z. Now you can see that the components of f are m, n and 0. Now this is equal to, now the first component will be minus I time minus del n upon del z. Then we will have minus j, this into this, minus this into this. So this will be a plus j into del m upon del z. Then we will have k times del n upon del x minus del m upon del y. Now in the xy plane your normal vector will be, now for the xy plane our normal vector will be k cap, and your ds will be equal to dx into dy upon modulus of n dot k cap, as your n is k cap, so this is basically equal to dx into dy. So your right hand side will be, so your curl double integral s curl of f dot n ds is equal to, now its projection in the xy plane will be your r, your curl f is equal to this one. Now if you put the value of n as k cap, then this curl f dot k cap will give you del n upon del x minus del m upon del y. Now curl f dot n cap, your n cap is k cap, so this curl f dot k cap will be equal to del n upon del x minus del m upon del y and into the value of ds, which is your dx into dy. So let us put these values in equation number 1. So by 1, hence by 1 you can see that your left hand side is equal to m dx plus n dy, and your right hand side is equal to the surface integral over the plane r del n upon del x minus del m upon del y into dx dy. So this is your proof of this Green's theorem for plane. Now let us verify this Green's theorem with the help of questions, and let us solve few more questions based on this Green's theorem. So our question number 1 is to verify Green's theorem for xy plus y square dx plus x square dy, where C is the closed curve of the region y equal to x and y equal to x square. So here we have to verify Green's theorem for this line integral, where C is the closed curve of the region y equal to x and y equal to x square. So solution. Now let us draw this region. You can see that this is your parabola. So we have this parabola and we have a intersection by the line y equal to x. So this is your y equal to x. This is your x square equal to 4ay. Now this intersection point will be, just put the value of y equal to x. So your x will be common. So we have x equal to 0 or 1. So this will be your 1. And again the value of y will be 1. And this is your 0, 0. Say this is your point O. Say this is your A. Say this is your long curve C1. Then say this is your long curve C2. Now for the surface integral, we will take a vertical strip. Now here we have to verify this Green's theorem. So your m is this one, your n is this one. So in our case, our m is equal to xy plus y square and n is equal to x square. Therefore, now let us evaluate the surface integral first. Therefore, your double integral r del n upon del x minus del m upon del y dx dy is equal to, now your del n upon del x will be 2x, your del n upon del y will be, now this will be your minus x, then we have minus 2y into dx into dy. Now we have to solve this double integral, and for that let us take the vertical strip, and for this vertical strip you can see that your value of y is from x square to x and the value of x is from 0 to 1. So here your x will vary from 0 to 1 and your y will vary from x square to x. Then in the bracket we have x minus 2y into dx into dy. Now as we have the limit of y in terms of x, so let us integrate this, integrating first to this respect to y. So on integration with respect to y, we will have xy. Now here we will have y square by 2, so we have this y square and the limits from x square to x, and then the integration with respect to x. Now this is equal to x equal to 0 to 1. Just put the limits. Here we have to put y equal to x, so we have x square. Again, this will be your x square. Now for the low limit, here we have to put y equal to x square, so this will be minus x cube. And then this minus will give you plus x power 4 into dx. And this x square and x square will get cancelled. Now if you integrate this x power 3, then this will be your x power 4 upon 4, so this will be your minus 1 by 4. This will be your x power 5 upon 5, so the limits will give you 1 upon 5. And this is equal to minus 5 plus 4 upon 20, and this is equal to minus 1 upon 20. So the value of the double integral is equal to minus 1 by 20. Now we will show that the value of the line integral is also minus 1 by 20. Now here you can see that this line integral is a sum of two line integral, one along the curve C1 and the other one along the curve C2. Now for this C1, your y is equal to x square, so our dy will be 2x dx. So let us put the value of f dot dr. Your f dot dr, this is your f dot dr, which is your xy plus y square. So say this is your equation number 1 and say this is 2. Now for C1, for this integral C1 f dot dr, our C1 f dot dr is equal to C1. Now this is your xy plus y square dx plus x square dy. Now for this C1, your y is equal to x square, so your dy will be 2x dx. So just put the value of dy. So this is your C1, your y is equal to x square. So this is your x square, so this will be your x cube. Your y is equal to x square, so this will be your x power 4. And then here we have dy, so your dy will be 2 into x into dx. So this will be your 2x cube dx plus 2x cube dx. And you can see that the limits of x for this curve are from 0 to 1. So this is equal to integral 0 to 1. Now this will be your 3x cube plus x power 4, and then the integration with respect to x. Now integration of x power 4 will be, x power 3 will be x power 4 upon 4, so this will be your 3 by 4. Integration of x power 4 will be your x power 5 upon 5, so we have 1.5. And this is your 19 upon 20. So the value of C1 is 19 upon 20. Now again, for the integral C2 f dot dr, the value of this integral C2 f dot dr will be equal to the line integral along C2. Then we will have xy plus y square dx plus x square dy. Now for this C2, your y is equal to x, so your dy will be dx. Your dy is equal to dx and your y is equal to x, so this will be your x square. Your y is x, so this is again x square. Your Again we have x square, your dy is dx, so this dx will come outside. Now for this curve C2, you can see that your limits of x are from 1 to 0. So this is equal to integral 1 to 0. Now in the bracket we have 3x square dx. Now the integration of x square will be x cube upon 3. So this 3 will get cancelled and this is equal to minus 1. Therefore by 2, hence put these values in equation number 2. So by 2 we will have the integral c f dot dr equal to, the first integral was 19 upon 20 and the second integral is 1. So we have 19 minus 20 upon 20. So this is equal to minus 1.20. So therefore you can see that by equation number 1 and by this equation number 3, your line integral is same as your surface integral. Therefore your line integral is same as this double integral. So we can say that our Green's theorem is verified. So our Green's theorem is verified for this question. Now let us use the Green's theorem to evaluate Green's theorem to evaluate the integral c x square plus xy dx plus x square plus y square dy, where c is the square formed by the lines x equal to plus minus 1, y equal to plus minus 1. So solution. Here we have to evaluate this line integral with the help of the Green's theorem. That means we will apply our Green's theorem for the double integral. That means we will use the double integral to evaluate this line integral. So solution. Here you can see that we have a square with x equal to 1. So this is your x equal to 1. Here we have x equal to minus 1, and then we have y equal to minus 1, and then again we have y equal to plus 1. So this is your square, so this is your x axis, this is your y axis, and here we have y equal to minus 1. At this point we have y equal to plus 1, here we have x equal to minus 1, and this is your x equal to 1. Now by Green's theorem, our line integral m dx plus n dy is equal to this double integral. So this is equal to this double integral. So from here you can see that this line integral c x square plus xy into dx plus x square plus y square into dy is equal to, now this is equal to double integral r del n upon del x. So this is your n, so this will be your 2x minus del m upon del y. So the integration with respect to y will give you x. So this is simply x, and the limits, your x is varying from minus 1 to 1, your y is varying from minus 1 to 1, and in the bracket we have x into dx into dy. Now the integration of x will give you x square by 2, and if you integrate with respect to y, then the integration of dy will be 1, and for upper limit we will have 1, and for the lower limit again we will have plus 1, so this will be 2 times. So 2 times, then we have x equal to minus 1 to plus 1, then x into dx. Now this is your odd function, so this will be your, and again you can see that the integration of x will be your x square by 2, and for the upper limit and lower limit it is your 0, and you can also write it as directly 0 because this is your odd function and it will give you directly 0. So the value of this integral with the help of the Green's theorem is equal to 0. Now our next question, to evaluate this y minus sin x into dx plus cos y into dy, where C is the triangle, where your C is the triangle formed by the lines y equal to 0, x equal to pi by 2, and y equal to 2 pi x. So we have these three lines, and for this triangle we have to evaluate this line integral. So solution, let us draw this triangle. So you can see that this is your line y equal to 0, so we have this line y equal to 0, then x equal to pi by 2, say this is your x equal to pi by 2 line, and then we have a line y equal to mx, say this is your y equal to mx. So this is your y equal to 2 pi x. Now your intersection, if you put x equal to pi by 2 here, then you consider your y is 1. So this is your pi by 2 comma 1, and this is your 0 comma 0, and again at this point we have pi by 2 comma 0. As we have to evaluate the line integral with the help of the Green's theorem, so we will use our double integral, and for that we will take our vertical strip, and you can see that for this particular strip your y will be from 0 to 2 pi x, and your x will vary from 0 to pi by 2. So by Green's theorem, the value of this is equal to, now this is your y minus sin x into dx plus cos y into dy, and this is equal to the double integral r. Now del n upon del x will be 0 minus del m upon del y. Now your del m upon del y, this is your m dx plus n dy, so this is your del n upon del x. The differentiation of this one with respect to x will be 0 minus del m upon del y. Now the differentiation of this one with respect to y will give you 1. So we have the area of this triangle. You can directly, as we have 3 points, if you wish to find out the area of a triangle, then you can directly find it with the help of the formula. But here I am using the double integration, and you can see that this is equal to, now here our y is from 0 to 2 pi x, and our x is from 0 to pi by 2 into dx into dy. Now the integration with respect to y will give you 2 pi x. So this is equal to 2 pi into x into dx. So we have minus 2 pi. Now the integration of x will be your x square by 2. So this 2 will get cancelled. So we have x square, and the square of this pi by 2 will give you pi square by 4, and so this is your minus pi by 4. So the value of this line integral with the help of So the value of this line integral with the help of our Green's theorem is equal to minus pi by 4. Although in my problem this was my cos x, but here I have written cos y. So for cos y, this is your correct answer. Now assume that if we have cos x here, then so let us assume cos x here. So if you assume it can be cos x or cos y. So if we have cos y, then your answer is equal to minus pi by 4. Now suppose that this is your cos x. Now if it is cos x, then again here we will have cos x. Now your del n upon del x will give you, now this del n upon del x will give you minus sin x, and then we have minus 1. Now you can see that this is a different question. Now for this question we have the double integral 1 plus sin x into dx into dy. Now let us apply the limits. So we will have 1 plus sin x dx into dy. This is your correct answer for your n equal to cos y. Now I am taking n as cos x. Now the integration of 1 with respect to, so the integration of dy will be your y, and for that we have this limit, and for that we have into 2 upon pi x into dx. So this 2 upon pi will come outside. So this is your minus 2 upon pi, and in the bracket we will have x into x plus sin x, and then the integration with respect to x. Now let us integrate this bracket. So the integration of x will be your x square by 2. Here we will use the product rule. That means we will use the by part integration. Integration of sin x will be minus cos x. Then we will have minus sin. And integration of cos x will be your sin x. So this minus and this minus will get you plus sin. And then the limits from x equal to 0 to pi by 2. Now this is your 0 for the both lower and upper limit. This upper limit will give you, here we will have pi square upon 2 into 2, that will be your pi square upon 4 into 2. So this will be your 8, and this sin pi by 2 will give you plus 1. Now if you send this minus 2 upon pi in the bracket, then we will have minus pi upon 4 minus 2 upon pi. This minus pi upon 4 plus 2 upon pi is your answer of this new problem. So this is our answer when we have taken our n as cos x. Now our last question is to verify Green's theorem. Again, verify or use Green's theorem. Use Green's theorem to find. Now with the help of this Green's theorem, here I will find out the area of a region. So here use Green's theorem to find the area of a region in the first quadrant bounded by the curves. This is your straight line. Then we have a hyperbola, and again we have a straight line y equal to x by 4. So let us verify Green's theorem. Let us find the area of a region in the first quadrant bounded by these curves. So let us draw these curves. So our solution, this is our line y equal to x. Say your hyperbola will be like this. say this is your y equal to 1 by x, and again we have a straight line y equal to x by 4. So this is your y equal to x. Now this intersection, now if you put y equal to x here, then you can see that your x square is equal to 1. So x will be your minus 1 and plus 1. I am taking the values in the first quadrant, so this will be your 1 comma 1. Again, this is your x y equal to 1. Again we have a straight line which is your y equal to x by 4. Now your intersection of this line, intersection of this hyperbola and this straight line will be equal to, put the value of y as 1 by x, so this will be your x square equal to 4, so your x will be plus 2 and your x is plus 2, so our y will be half. So this is your straight line and this intersection point is 2 comma half. This intersection point is 1 comma 1 and this is your origin. Now here we have to find out the area. Now what is your area? By Green's theorem, we have this line integral m dx plus n dy is equal to this double integral. So this is your Green's theorem. Now for the area, this has to be 1. The value of del n upon del x minus del m upon del y should be equal to 1. So now let us try to make this bracket as 1. For that, let us put n equal to x and m equal to minus y. Now then you can see that this del n upon del x will be 1 and this del m upon del y will be again plus 1. So this will be plus 2 and this 2 will come this side. So this will be your area. Now let us put these values here. Then in the left hand side we have c. Now your m is minus y, n is plus x. So we have x dy minus y dx. Now in the right hand side we will have double integral over r. Then this bracket is equal to 2 into dx into dy. So your area, therefore area equal to dx into dy is equal to, now your dx into dy will be half the integral over c x dy minus y dx. Now we will write this line integral. Now here you can see that your line integral will be, say this is your curve c1, say this is your curve c2 and say this is your c3. So in our case this will be your sum of the line integral along c1, then the line integral along c2, then our line integral along c3. So we have these three line integral. Now let us evaluate these line integrals one by one. So for the first part, that means for c1, we have y equal to x by 4, so your dy will be dx by 4. So just put the value of dy and your x will be from 0 to 2. So I am directly putting the value here. So for first part, your x will be from 0 to 2. Your y is equal to x by 4, so your dy will be dx upon 4. So this is your x into dx upon 4 and your y is x by 4 into dx. So this is your first integral. Now for the second part, that means for c2, your y is equal to 1 by x, so your dy will be minus 1 upon x square dx. Now for the second part, and your x will be from 2 to 1. So here our x will be from 2 to 1. Your y is equal to 1 by x, so your dy will be minus 1 upon x square. So this is your minus 1 upon x into dx. Again we have y as 1 upon x, so this is again 1 upon x into dx. And our third integral, that is along C3. Your y is equal to x, and the values will be from 1 to 0. Your y is equal to x, so your dy will be equal to dx, so this is your x. Your y is x, so our dy will be dx, and your y is x, so this is your x into dx minus x into ds. So this term is 0. Now the integration of first part, this is your 4x minus x, so this is your 3x by 4. So this will be your 3x upon 4, so this will be 3 upon 8. Now the integration of x will be x square by 2, so we have 1.2, and x square is 4. So this is your first term. Now in the second term, this is your minus 2 upon x, so this 2 and this 2 will get cancelled. So we have minus and then integration of log x. That means the integration of 1 upon x is log x, and the limits from 2 to 1, and the third part is 0. So you can see that this is your 3 by 4, and here your log will be 0 and your log 2, so we have minus plus. So this is your 3 upon 4 plus log 2. Again we have done a mistake here. For this part, your dy, for this first part, your dy will be equal to dx upon 4. So this is again your x upon 4. So again this for this part, first part, your value is 0. So this is equal to, this first part is equal to 0. Here we have, this was your what? This was actually x dy. So your dy is dx by 4. So this will be your x by 4. So again this is 0. The third term is 0. And we have just second term, and this is your minus 2 upon x, so this 2 will get cancelled, so we have minus 1, and integration of 1 upon x will be your log x, and then the limits from 2 to 1, and this is your log 2. So this is the solution of this problem. So that means the area bounded by these three lines or these three curves is equal to minus log 2 plus log 2. So this is all about this engineering mathematics 1. Today I have completed the syllabus of Engineering Mathematics 1. Thank you so much for joining these lectures.